Okay, so in this video I'm going to talk about a project I did in 2021 as part of the Quantum Engineering Centre for Doctoral Training that I'm in, and it was about quantum compilation, and it was in collaboration with the ION Quantum Technology Group at the University of Sussex. Okay, so before we go into everything, we'll talk about a little bit of motivation, and as with everything with quantum in front of it, it's easier if we start off by talking about the classical version. So what is classical compilation? Well, it's essentially this idea of taking a high-level programming language, so something like Python, and turning it into so-called machine language, which is a nice way to think about that is just what can the computer understand? And that's what we hear of as the zeros and ones. So we're essentially turning something like print hello world, which is a line you might see in a Python program, and it will convert that into the appropriate string of zeros and ones. I'm not sure if this is right, it's probably not. In fact, it's very likely not right. Okay, so what is quantum compilation? So now we're just going to do the same thing. We're going to take some high-level quantum algorithm, which in our case is just going to be a random n-qubit gate, so a unitary matrix on n qubits, and we're going to turn it into a set of instructions that we can actually perform on a quantum computer, and we'll get into that a little bit later. So if we think about what a quantum algorithm on n qubits is, it's essentially just going to be an n qubit unitary matrix. So if we've got a bunch of different gates on a bunch of different qubits, we can just sequentially and what's the other word for sequentially? Use the tensor product to mush all of these unitaries together into one big unitary on all n qubits. So we can think about an algorithm that we want to implement just being a big unitary matrix, and then we say, okay, we want to execute this algorithm on a quantum computer. How do we do that? Can we just implement this gate as it is? And the answer is no, and the reason is that each quantum computing platform, like trapped ions, superconducting qubits, or photons, can only implement specific quantum gates. And those specific gates are usually going to be broken down into a single 2-qubit gate, which can entangle 2 qubits together. And then we're going to have access usually to 2 single qubit gates, which will be rotations on the Bloch sphere along 2 perpendicular axes, but we are allowed to rotate by those axes around any angle. So we've got single qubit gates, 2 perpendicular ones, which can be any angle, and a singular 2-qubit gate. And thankfully, it turns out that if we have those things, we can approximate any 2-qubit gate to arbitrary accuracy. And then, thankfully again, it turns out that any n-qubit gate can be approximated by a number of these 2-qubit gates. So essentially what this means is that we can take an arbitrary n-qubit quantum gate, or in other words, an algorithm that we want to perform, and we can approximately implement it using just 2 single qubit gates and a 2-qubit entangling gate. And by that I don't mean 2 instances of the gate. There's going to be multiple repetitions of single qubit gate 2, 1, 1, 1, and so on. We're going to be chaining a bunch of these rotations together. So here what we're saying is basically what I've just said, but a little bit more neatly. So any n-qubit gate can be exactly decomposed into products of arbitrary single qubit gates and a 2-qubit entangling gate, for example a C0. And the reason that I've said can here is because we can exactly decompose it if we want to, or we can approximately decompose it. And it just depends on the number of the 2-qubit entangling gates, in this case the C0, we use. And you might be thinking, well, why would we approximate it if we can exactly decompose it? And we'll come on to that later. So in this first point, we're saying that we need arbitrary single qubit gates, and it turns out that arbitrary single qubit gates, which is something that we're not going to have access to on quantum computers, so that would be a rotation about any angle by any axis. So we don't have that, but what we are going to have is rotations about 2 axes on the Bloch sphere. So let's say maybe this axis and this axis, and we can chain rotations about 2 perpendicular axes together to approximate a rotation by any angle along any axis. Okay, so the actual project that I did was this thing called a quantum volume calculator, and as I was working with the ion group in Sussex, it was within the context of their trapped ion quantum computer, which is a little diagram of what it might look like is shown here. So essentially we've got these trapped ions which act as qubits, and they get shuttled around this like matrix looking thing here. And if we want to perform a 2-qubit gate on particular qubits, we shuttle them next to each other and we perform a gate here, and then maybe we shuttle them next to other qubits, and so on and so on. And that's how we perform these 2-qubit gates or single qubit gates, and eventually these all crumple up together sequentially or using the tensor product to approximate our quantum algorithm that we want to perform. So here's the steps. So what we're going to do, we're going to have some fixed number of qubits, we're going to randomly pair them, we're going to shuttle them close to each other so that we can perform a 2-qubit gate, and then we're going to perform random 2-qubit gates on these pairs, and then if there's an odd number, we'll just put a random single qubit gate on that one, just so it's not left out. And then we're going to keep doing this until we lose coherence. So that's essentially what our quantum volume calculator is going to do. So here's a look at what the decomposition of a single 2-qubit gate might look like in Qiskit, which is what we built this in Python. So here I've got 2 qubits called Q0 and Q1. I implement a random 2-qubit gate on the 2 of them, shown here, and then I measure the 2 qubits. So ideally, I would be able to just implement this arbitrary 2-qubit gate in real life on a quantum computer, but that's not possible. And the reason is because each quantum computing platform has what's called a native gate set. So that is what the computer can actually implement. And in the case of a trapped ion quantum computer, what we have access to is a Malmer-Sorensen gate, which is the 2-qubit gate. So it belongs to the SU4. And then we also have arbitrary rotations about the x-axis of the block sphere and the y-axis of the block sphere. So we're fixed in the axis that we can rotate in, either x or y, but we have full access to the angle that we rotate by. And it turns out that this set here satisfies the criteria that I had 3 slides ago, which basically means that I can, with these 3 operators or gates, I can implement any SU4, so any unitary in SU4. And then again, one step up, we think about what we actually want to implement is a unitary on SU 2 to the n, so for n qubits, so any unitary on n qubits, just another way of thinking about a quantum algorithm. And it turns out that if I can do this, if I can approximate any 2-qubit gate, then through chaining these together and using the tensor product, I'm able to implement any n-qubit gate. Okay, nice. So as I was saying, here I've got a random 2-qubit gate between 2 qubits called Q0 and Q1. And as I just said, if I'm able to approximate this thing, then I can essentially approximate any n-qubit gate or any quantum algorithm. And what this code does is it takes this random 2-qubit gate and it just decomposes it into the native gate set of the trapped ion quantum computer. So you can see here it's decomposed it into x's, y's, x's, and then this rxx thing is just the Malmer-Sorensen gate. And then we've got more y's, more x's, more Malmer-Sorensen. So everything here can actually be implemented on our trapped ion quantum computer. And then you might be wondering what this first gate is here, this rotation about z by 0 degrees. Essentially, this thing just implements the shuttling of the ions that we were talking about. And the reason why this is in there is because each of these gates actually has some stochastic error associated with it. So when I implement a gate in real life, there's going to be some probability of something messing up. And this code actually uses real world data from the trapped ion quantum computer at Sussex, and it implements a realistic error on each one of these gates. And as we would expect, the 2-qubit gates have the most error, and then the single qubit gates have about a factor of 10 less. And then the this shuttling operator here, which is basically just the identity, just a rotation by 0 degrees, but it's in there so that I can add in some potential loss of coherence as we're shuttling the ions close together. Here's a little bit more of a mathematical breakdown of what we're actually doing. So again, just to drill the point home, if I can decompose a random 2-qubit gate into our native gate set, then I can implement any quantum algorithm using that native gate set. But there's going to be various errors going into that. So there's going to be the error in approximation. Can I chain these gates together to exactly get the operator that I want? In most cases, no. And also, like I just said before, when I physically implement these gates, there's going to be error associated with them. So it turns out that the more gates that I plug into this chain, the closer I'm going to get to the unitary that I want to implement. However, the more of these gates that I perform, the more error is going to accumulate, because each one has some amount of some probability of error, and then the more I use, the probability of error in total goes up. So basically we're using this thing called CAC decomposition, and essentially all it does is it takes our 2-qubit unitary and we decompose it into single qubit gates, a 2-qubit gate, single qubit gates, 2, single, 2, and single. And this here is an exact decomposition. So this chain here, if I have the correct single qubit gates, will exactly be exactly the same as the arbitrary 2-qubit gate that I want to implement. However, as we said, we don't have access to these arbitrary single qubit gates. I only have X's and Y's, which is why if I look back at this slide here, you'll notice that this whole thing here is the same as this thing here. So this K1A gets broken down into these three single qubit gates. And again, so if I want to exactly decompose it, I need, in this case, to use 3 instances of the C0 gate, but I can also just approximate it if we imagine that, for example, I got rid of, let's say I got rid of all of this stuff here at the end, and I just have these two qubit gates, then this would then be some approximate decomposition. Okay, so now I've done a brief run through of the theory, we'll look on to the code that I wrote that actually implements all of this stuff. Okay, so now I'm going to move on to the part of the video where I'm actually going to go through the code. So this is the Jupyter notebook where everything is in, and I've got a little bit of an explanation of things at the start here. So let's have a look. What is classical compilation? So as we said before, we're just taking, in the classical case, we're taking a high-level programming language like Python or C++ and converting it into machine language, which is what the computer can understand, and it's the zeros and ones that we hear about all the time. So what's quantum compilation? So we're taking a high-level quantum algorithm, which is going to be an arbitrary unitary on n qubits belonging to SU 2 to the n, and we're going to decompose it into a set of gates that we can actually perform on a quantum computer. Why do we need to compile? Why can't we just implement this single unitary operator? Wouldn't that be nice? And the answer is that there's basically just no proposed way to do it. Quantum computers at the minute are struggling to even implement the single and 2-qubit gates that we're at. So to all of a sudden want to implement n-qubit gates, I just think it's a case of good luck trying to do that. So another thing, I can write you a quantum algorithm and you can then implement it on multiple different platforms. You could choose trapped ions, superconducting photons, superconducting qubits or photons. And each of these have their own pros and cons. So some have good coherence time, some have good gate fidelity, some have good measurement fidelity. As far as I'm aware, none of them are perfect. There's trade-offs involved in them all. And similarly, they all have their own native gate sets. So the gates that you can actually perform on Google's Sycamore chip are not the same gates that you can perform on, say, a trapped ion quantum computer. So that means that we need to compile into different native gate sets. So this native gate set needs to be what we call universal, which just means that any unitary can be approximated to arbitrary accuracy using chains of gates in the set. So if you give me rotations by x and y of arbitrary angle and a 2-qubit entangling gate. That's a universal gate set, so any unitary on n qubits can be approximated using chains of gates in that set. So as we said before, what we want to do is decompose a quantum algorithm, which is a unitary on n qubits. And now we're going to look at the different steps involved in that. So if we look at reference 1, which is Nielsen and Chang's textbook, we find out that any unitary can be exactly decomposed into what are called 2-level unitaries, which are unitaries on n qubits, but they only act non-trivially on 2 basis states. And then it turns out that these 2-level unitaries can be approximated by just 2-qubit gates. And then it turns out that 2-qubit gates can be approximated through CAC decomposition, which was in the final slide of the presentation at the start, which is into arbitrary single-qubit gates and a 2-qubit entangling gate. And then it turns out that those arbitrary single-qubit gates can be decomposed as long as we have arbitrary angle single-qubit gates along 2 perpendicular axes on the Bloch sphere. So as long as we've got 2 arbitrary axes on the Bloch sphere that we can rotate about by any angle, and we have a 2-qubit entangling gate, through all those different steps of decomposition, we can approximate any quantum algorithm. Okay, so there's going to be some trade-offs in compilation. We've said that the longer the chains are in our approximation, the closer that chain will represent the thing that we're trying to approximate. And then you might say, well, why don't we just make the chain really long? And the answer is because it'll take a long time to implement in real life, and the qubits only have some finite coherence time. And also, every time we implement a gate physically, there's some probability of error. And if you implement loads and loads and loads of gates, if your error is anything but trivial, then that error will accumulate, and the thing that you're approximating in real life isn't going to look like what you want it to. So there's some trade-off between using as many gates as possible to get as close as possible theoretically, and then the real world kicks in and it says, well, each one of those gates is going to have some error with it, so you need to pick your poison, really. So now we'll talk about how this code actually works. What is this quantum compilation simulator actually going to do? Basically, we're going to choose a number of qubits, and then we're going to choose a circuit depth, which that will become clear in a second. And each layer in this depth, what we're going to do is take all the qubits, we're going to randomly pair them together, and then we're going to execute random 2-qubit gates between those pairs. And then we're going to decompose each one of those gates into the native gate set. And then in the next layer in the depth, we're going to do the same thing again. We're going to randomly pair them, random 2-qubit gates, decompose them into the native gate set, so on and so on. And then we're going to we're going to run multiple instances of this circuit. One of them where we implement the 2-qubit gates without any decomposition. So this gives us the ideal quantum circuit. No decomposition. In a perfect world, if we could just implement gates as we like, what would the final outcome look like? And then we're going to decompose all of the 2-qubit gates using no instances of the 2-qubit entangling gate. 1 instance, 2 instances, and 3 instances. So 3 instances of the 2-qubit entangling gate in CAC decomposition gives us exact decomposition. So ideally, that should be exactly the same as the original quantum circuit that we're going to implement, where no decomposition happens. However, what we're actually going to do as well is each time we implement a gate physically, we're going to add some error. So there's going to be some error when we implement single qubit gates, some error when we implement 2-qubit gates. And something I forgot to mention is in between each depth layer, we're also going to shuttle the ions around. And there's going to be some coherence error that goes into that as well. And there's also going to be some measurement error too. And all of these errors come from actual experiments that were done on the quantum computer at Sussex. And then we're going to compare the ideal state with the states from the 4 different methods of decomposition, and we're going to see which one gives the best fidelity, and then we're going to say that that's the that's the decomposition method that we should use. So this work isn't perfect, and one thing that is wrong, that's a spelling mistake. So there's multiple things that are wrong. But essentially what's happening is I'm choosing a fixed decomposition, where it would be nice instead to have the ability to say on the first 2-qubit gate, let's decompose that one exactly, and on the next one maybe I only need to use 2 entangling gates, and on the next one I only need to use 1. So that's definitely a drawback of this. And another is that it's currently only set up to have the native gate set of trapped ions, but in principle it should be fairly easy to change it to another native gate set. Okay, so I'm gonna run through everything now. This is just all important stuff. This defines how we build the circuit. These functions here define how we recombine the decomposed gates back together. So here we choose our basis 2-qubit gate, which is the Malmer-Sorensen, and we choose the single qubit gates, which are the X's and the Y's. Here's a bunch of data that comes from actual experiments, which gives us single qubit errors and 2-qubit errors. Okay, so here I choose the number of qubits and the depth. So to start with, I'm just going to choose 2 qubits and depth of 1. So these 2 qubits are going to get paired together. It's going to create a 2-qubit gate between them, and then we're going to decompose it. So here I'm choosing the 2-qubit gate fidelity, the single qubit gate fidelity, coherence times, and the amount of time it takes to shuttle. So how long does it take to get the qubits next to each other? And the rest I'm not sure is too important. Here we add in some errors, so we've got some thermal noise and we've got some operation noise. So this basically just means when I implement a gate, what might go wrong. So let's say here, so maybe I accidentally perform an X gate, or I accidentally perform a Y or a Z or an identity, and all these have associated errors with them. And yeah, so here we add errors for decoherence and shuttling. We've finished. And then this is where we actually get to the interesting part. So let's wait for this to run. So in this particular case, it tells me that I'll get the best state fidelity if I use 3 basis gates in my decomposition. The fidelity will be about 99%. And then here we can compare the states for the ideal in red and the decomposed circuit in blue. So it's not looking too bad. Here I look at my ideal circuit, so I just want to implement a 2-qubit gate. And then this is what my decomposed circuit looks like. So I shuttle them together, I perform various X and Y's on each qubit, a 2-qubit gate, X and Y's again, 2-qubit gate, X and Y's again, and there's my third 2-qubit gate, and then X and Y's again. Hopefully that first little example made sense of just using 2 qubits and a depth of 1. So now let's see what happens. Let's say I up to 6 qubits and I have a depth of 4. So now what's going to happen is I'm going to randomly pair these 6 qubits together, implement a random 2-qubit gate, decompose it, run the circuits, and then I'm going to do that 4 times. That's what depth of 4 means. So let's run the full thing and see what we get out. So that took a little bit longer to run because now we're simulating a much larger Hilbert space. So interestingly now, look, we're saying that we're going to get the best state fidelity if we decompose all of those 2-qubit gates using 2 instances of our entangling gate rather than 3. And this is where the trade-off between more gates being a better approximation, but more gates also giving you more error. So here we're seeing that 2 gates is actually better than 3 because of the error associated. So the fidelity is quite low, 80%, and then here we can compare the different elements of the density matrix of the final state. It's a little bit hard to see because this is such a large density matrix. So here we see our ideal circuit. So we can see we've got paired qubits here with arbitrary 2-qubit gates. And then this is what our decomposed circuit looks like. So it's much larger, and yeah, this is where all the error comes from, because each time we implement one of these gates, something might go wrong. Okay, hopefully that has made sense, and if anyone's interested about this work or about this code, please just feel free to reach out to me. I'm happy to talk about it more or to send you the code if you would like. So thank you for watching.